In today's lesson, we are going to be looking at sketching quadratic functions with transformations. So in the previous lesson, we did a little bit of an investigation where we looked at how the transformations affect our quadratic or the base form or the most basic form. And now we're going to be looking at sketching these transformations given a transformed function. So a little bit of a review, right? The most basic form of a quadratic that we know is f at x is equal to x squared, or you could rewrite it just as y equals x squared, whatever your preference is. F at x or x squared. F at x, again, is just the function notation. There are 5 key points to our quadratic. Right? We had -2 and 4, we had -1 and 1, we had 0 and 0, 1 and 1, and 2 and 4. Those are the 5 key points that we're going to use, and we are going to use them, and we're going to need to know them when we look at these transformations and how to come up with these transformations or sketch the transformations. F at x equals ax minus h squared plus k. This is our vertex form. This is the form that we're going to be using when we're dealing with transformations. In the previous lesson, you looked at a, h, and k and how it affected the base function. So just kind of a review of that. A, it stretches if a is greater than 1, or compresses if a is between 0 and 1, so if a is a decimal. It flips our function if a is negative. And all of these values, in order to stretch or compress or flip when a is negative, what this is actually doing, and this is going to be the important part that we need to kind of highlight or remember, that this a value multiplies the y value. So the a value multiplies the y value, and that's what causes this stretch or compression or this flip. And we'll talk about that in a second when we look at some examples. Our h, the h value, this is left or right. So it shifts left if a is negative, or if a is less than 0. I'll just put a as negative just to make it easier. Negative or right if a is positive. And again, the important part, what is this actually doing to our function or to our values? And so essentially what we do here is the x value, so our x value has h added or subtracted. So essentially we're adding or subtracting h to our x value, and that's going to cause our shift left or right. And finally, our k value shifts our function up, so shifts it up if a is positive, or down if a is negative. And again, the key part here, this y value or the y value has k added or subtracted, depending again on what it is. So that addition or subtraction is what's going to cause our function to move up or down. If we're adding, or if I keep on writing, I've written a's on all of these, but this should be h and this should be k. So if I add If k is positive, I'm going to add it to the y value, and that's going to cause a shift up. It's going to increase the y value and cause it to move up however many units that k is. If it's negative, I'm subtracting, and it's going to move my y value down. So to graph a quadratic function in the form g at x is equal to a x minus h squared plus k, or basically our transformed function, the effects of a, h, and k on the graph of f at x equals x squared, or basically the transformations that apply to our parent or base function, are applied to each point belonging to the original function. So this is what we refer to our key points as. So this is why it's important to know our key points, because those are the points that the transformations are being applied to, which I just kind of mentioned underneath. Applying each transformation to the 5 key points, I'm going to erase that because we just restate it, we end up with the transformed function. So after we apply those transformations, we end up with the transformed function. So let's take a look. So first we want to sketch the parent function f at x equals x squared, then determine the transformations and apply them to the key points. And finally, once we apply those changes or those transformations, we're going to sketch the transformed function. So the first one is going to be our parent function. Right? This is going to be our f at x equals x squared. So these are going to be our key points. So -2, 4, -1, 1, 0, 0, 1, 1, 2, and 4. So I'm going to plot those values on my graph. And now I have my transformed, or my parent function. So this is the parent function. For the transformed function, we have to then think about what are the transformations that we're going to be applying. Or in other words, what are the a, h, and k values that are different or that have been added to this transformed function. The only 2 values that I see that are different from this parent function up here are a +2 inside the bracket and a +1. So the +2 is our h value, and it's opposite of what we see. So the fact that we see a +2 means that h has to be -2. If we have a -2, this means that our graph is moving left 2. An h here so we know where it came from. The other value we have is k. K is equal to +1, so this means we move up 1. So now we can go and look at our points. So these points are going to change, and how they're going to change is if I'm moving left 2, that means the x values are going to be subtracted by 2. So I'm going to subtract 2 from every x value to get my new x values of the transformed function. So -2 minus 2 is -4. -1 minus 2 is -3. -2, -1, 0. So in this transformed function, all of these x values are now 2 to the left. So I've shifted everything to the left 2. Now I'm going to look at my k value. Because the k value is a +1, that means I'm moving up 1. That means that all of my y values are going to increase by 1. So 4 plus 1 is 5. 1 plus 1 is 2. 1, 2, 5. So now I have my 5 key points for the transformed function. Now that I have these, now I can go through and graph them. So if I go through and graph them, -4 and 5, -3 and 2, -2 and 1, -1 and 2, and 0 and 5. So now I've graphed my function. This red one is the transformed. And we can see from the key points, compared to the parent function, this function in red has been shifted to the left 2 and up 1. So that is now my transformed function. So it's going to take some practice to get used to finding what the h and k are and understanding how it affects our values. But we're going to look at a couple more examples that hopefully covers all the bases so we are comfortable going forward. So for the next one, it's going to be the same thing. We're going to graph the parent function, and then we're going to look at our transform function, determine the transformations, apply them to the key points, and then sketch. So for the first one, again, for the parent function should be the same. So -2, 4, -1, 1, 0, 0, 1, and then 4. So again, I can quickly go through and graph that for my transformed function, or sorry, my parent function. Now I need to figure out what are my transformations. What are the a, h, and k that are different from this parent function? Basically, what values am I seeing that are different, or what is different about my new function down here that we don't see in this parent function? Well, the two things that we see are 2 and this -3. So there's two different functions that we see here, or two different transformations. We have an a value of 2, of +2. So when a is positive, if we remember from the lesson from yesterday, this means that we have a stretch. And what we say, we have a stretch by a factor of 2. And this basically just means we are multiplying our values by 2, or the y values by 2. We have an h value here. And because h is negative in the equation, that means h is actually positive, which means we go to the right 3. So I'm going to go through and now come up with my table of values. Now in this case, the two transformations are affecting different components of our key points. The shift to the right, that affects the x value. Right? When we talk about shifting to the left or right, that's talking about changing our x value of our points. So because it's saying to the right 3, that means each of our x values, we are going to add 3 to them. So -2 plus 3 is 1. We have 2, 3, 4, and 5. When we talk about a stretch by a factor of 2, that means we're multiplying everything by 2. And when we're talking about changing, is we're going to be changing the y value. So that means we're going to take each y value and multiply it by 2. So 4 times 2 is 8, 1 times 2 is 2, 0 times 2 is 0, 2, and then 8. Now I have my transformed points. So now I can go through and plot these points at, we have 1 and 8, 2 and 2, 3 and 0, 4 and 2, 5 and 8. And now I can graph my points, sketch it, and I have my transform function. So if I look at these points, or if I look at these two graphs, I can clearly see the shift to the right 3. The function in red has been moved to the right 3 units. All the points have been shifted to the right 3. The stretch is a little bit harder to see, but we should see that it does appear to be more narrow. Right? So this function in red does appear to be more narrow because we stretched it vertically. So imagine kind of grabbing the top and the bottom of something and pulling it in either direction, right? Almost think of like an elastic or a rubber band, right? Where we're pulling from either end. Or if you think of like one of those Stretch Armstrong toys, if you've heard of those, it basically stretches and it gets distorted and the features get exaggerated. Similar idea here, right? We're stretching it vertically. We're pulling our values. All the values where they originally were are now doubled, right? So instead of being at 1, they're at 2. Instead of being at 2, they're at 8. At 0, it doesn't affect anything because 0 multiplied by 2 or 0 doubled is still 0. So that's what we mean when we talk about a stretch by a factor of 2. We're doubling the values for the heights, right? or the vertical stretch. There is such thing as a horizontal stretch, but we're not going to get into that in this course. You might see that in other courses, such as the 3U course. But we're just going to stick with our A, H, and K. Last example, same idea. We're going to go through, we're going to come up with our parent function, which we should already know or be kind of familiar with because we've done it 3 or 4 times, or we've done it 3 times already, or twice, but we've written out the points more than that. So -2, 4, 1, -1, 1, 0, 0, 1, 1, 2, 4. I'm going to go through, quickly sketch that. And now I have my parent function. Or I can call it f of x. So instead of the parent function, I can say this is f of x. Change it over here. And g at x is going to be the transformed function. But before I come up with the transformed function, I need to figure out what are my transformations. Again, we're seeing what values or what new things are we seeing that are different from this f of x equals x squared, right? What's the a, h, and k value? So if I go and look at my transformed function, I see this negative 0.5 and I see this plus 4. So this tells me that I have 2 values or 2 transformations at least to deal with. I have an a value and I have a k value. Right, keep in mind that is not the h value, it is not in the brackets. Right, so that is a and k. So an a value, which is negative 0.5, tells us actually 2 things. One, the sign. We'll start with that. That's an easy one. The sign, right? So because a is negative, that means it is flipped. And what we're doing when we're flipping this is we're just making all the y values negative. Or y values times -1. The other thing we have is the actual number, 0.5. So because it's between 0 and 1, this actually means we have a compression, and we'd say by a factor of 0.5. Or in other words, we're kind of shrinking everything. We're squeezing things together. We're compressing it. So that's our a value. And our k value, k is plus 4 or positive 4, which means we shift up 4. Now the interesting thing with this is all of these values or all of these transformations are affecting our y value. Right? The shifting up and down, that affects the y. The stretch or compression affects the y, as does the flipping of our function. So one thing we have to keep in mind when we're applying these functions is bed mass. Right? We have to keep in mind of what bed mass is because that is going to tell us the order that we do these transformations. So we're going to take each value or each y value. Let me actually just write out the x's so we don't forget those. Those are not going to change, but the stretch, the flip, the compression, the flip, and the shift up are all going to affect the y. So we're going to multiply our y value by negative 0.5, and then we're going to add 4. So 4 times negative 0.5 is negative 2, plus 4 is positive 2. 1 times negative 0.5 plus 4 is 3.5. And the same thing, we're going to multiply by negative 0.5 and then add 4. Times negative 0.5 plus 4 times negative 0.5 plus 4, we're at 2. So now I have my transform function from the transformations. I'm going to go through now and plot my points. So negative 2, 2, negative 1 and 3.5, 0 and 4, 1 and 3.5, positive 2 and 2. I'm going to connect my line or my points. I'm going to form this parabola shape. And we can see now by looking at it, hopefully we can easily see, let me just make this a little bit nicer here. Hopefully we can at least see the shift up 4, right? We can see the vertex. That's a nice easy one to see that shift. It's shifted up 4. And we can see by looking at it that this graph looks a little bit more compressed. So again, imagine that rubber band or imagine something like a pop can. If you're compressing it, that means like you're putting pressure, you're squeezing on the top and the bottom, and it becomes flatter or flatter but more wide, right? So if we look at our quadratic function, right, we can see that it's looking more kind of wider, so to speak, and our values are closer to the vertex than what they were. Right, so this is what we call the compression. Right, it's a vertical compression. We're basically taking the top and the bottom of our function and kind of compressing it together. So it's kind of coming up again with this kind of squished or shorter and wider appearance. So that was looking at transformed function and trying to come up with the transformations and applying them to the key points to graph or sketch our transformed function. So we've seen different examples of the A, H, and K. We've seen all the different variations of them. So hopefully you have some examples here to kind of help you through that. The last little example we're going to look at is given the transformations, can we come up with the actual function? So we're just basically going to go through, read the transformations, and figure, okay, what does that tell us about our function, or what does that tell us about the A, H, and K? So just remember our general function would be f of x is equal to a x minus h squared plus k. Again, that doesn't necessarily mean we're going to have something for every variable, but we should be looking for, do we see those transformations in the description? So first one we see is that it opens downward. Opening downward is another word for basically saying that it's flipped. So because it's flipped, that means the a value has to be negative. So we have to have a negative a. If it's narrower than f of x equals x squared, this is another way of saying that it's stretched. And in order for it to be stretched, the a value has to be greater than 1. Our vertex is negative 2 and 0. So if we think of the parent function vertex, the parent vertex was 0, 0. So how is the new vertex different? Well, it's minus 2, so that means our h has to be minus 2 because we've moved 2 to the left. So that means our h value has to be negative 2. Because the y value is 0, that also tells us that our k value has to be 0. So now that I have all this information, I can write my transform function by plugging in the values for the variables. So f of x is equal to, it has to be a negative a, it has to be greater than 1. For the sake of argument, let's just say it's 2. That's greater than 1. It could be 1.5, it could be 1.4, it could be 100. That would make it narrower. So because so we have our a value negative, it's 2 because it's stretched. We have our x, and because we have a minus 2 for our h value, that's the same thing as saying minus 2 in the brackets squared, but I can change, or I can rewrite minus a negative as just plus. So plus 2 squared, and then I could put plus 0 after for that k value, but I don't need to show that because it doesn't really affect anything. So then my transform function is going to be this. F of x is equal to negative 2 times brackets x plus 2 squared. Now that negative 2 up front, that 2 could change numbers. It could be anything as long as it's greater than 1. There's no stipulation, or it doesn't say what it's stretched by, so we don't have a specific number to put in. For B, the fact that it opens upward means we have a positive A. Congruent means no stretch or compression. So if there's no stretch or compression, A stays as 1. So if there's no stretching or compressing, our A value is going to be 1. That's technically the value in the basic form. The A value is 1. Our vertex is 4, negative 3. So again, looking at the parent vertex, which is 0, 0. If it's 0, 0, what has changed, right? So our H value is going to be a positive 4 because our vertex is 4 for the X value. So that means it's shifted to the right 4. Because our vertex, then the Y value is negative 3, that means we've shifted down 3 from our parent function. So that means K is minus 3. Now that I have all my pieces, I can write out my transformed function. F at x is equal to, I could say 1 and then x minus 4. Because again, remember the basic function or the general form for transformations has x minus h. So it should be opposite of what we see. So if it's a minus 4 in the equation, the h is a positive 4. Then squared, and then we just put our k value, which is minus 3. So that is our transformed function. Now I don't have to put that 1 in front for a. I could just leave it without. That would still work as well. If you want to put the 1 just to get in that general habit, you're more than welcome to, but it's not necessary, and it just adds more clutter to our function. So hopefully from this you're a little bit more comfortable with understanding the transformations. Again, do try to practice to get more comfortable sketching these transformations, understanding how the A, H, and K affect our values. And then being able to kind of work backwards and come up with functions based off a transformation.